These are iron filings, tracing the invisible contours of a magnetic field in the physical world. When you run a steady electric current through a wire loop, it generates a field that, up close, is a complex web of curving arcs. An electric dipole, a pair of opposite charges, creates its own distinct field of lines moving from positive to negative. But as we move further away from the source, the magnetic field of the loop and the electric field of the dipole become structurally identical. At a distance, the geometries overlap perfectly. This visual coincidence suggests a mathematical symmetry between electricity and magnetism that we can verify through the underlying equations. This is the textbook equation for the magnetic field exactly on the axis of a circular current loop. It calculates the field strength, B, using the loop's radius, r, and the distance from its center, x. To see what happens at a distance, we define the distance x as vastly greater than the loop's radius, r. On this scale, the effect of the loop's radius in the denominator is minimal. We remove the r² term, and the bottom of the fraction simplifies to x cubed. Next, we multiply both the top and the bottom of the fraction by pi. We can now group pi and r² together, which represents the physical area of our circular loop, denoted by A. By observing the loop from far away, the chaotic details of the field vanish. Its strength is now defined only by its current and its geometric area. This combination of current multiplied by area is what physicists call the magnetic moment. We replace the current and area variables in our simplified equation with a single variable for the magnetic moment, m. This creates a direct mapping between the forces. The electric field becomes the magnetic field, the electric dipole moment becomes the magnetic moment, and the permittivity of space is replaced by magnetic permeability. Substituting these variables into the existence equation for an electric dipole yields the exact equation for our magnetic loop. Because the structures are identical, physicists can predict magnetic fields at large distances by applying the same math they use for electrostatics. While the math between the electric dipole and the magnetic loop is perfectly aligned, the physical reality is not. An electric dipole is composed of two independent units. The positive and negative charges can be physically separated into stable individual particles. But consider what happens if we attempt to split a current loop in half to isolate a north or south magnetic pole. Breaking the physical wire loop instantly breaks the circuit. The flow of current stops completely, and the surrounding magnetic field evaporates entirely. This reflects a distinct property of our universe. Isolated electric charges are common, but isolated magnetic poles, or monopoles, do not exist. This limitation isn't just a property of wires. It applies to permanent bar magnets as well. On an atomic scale, the magnetism in a solid material is generated by electrons orbiting nuclei and spinning in synchronized loops. This led André-Marie Ampère to suggest that all magnetism is the result of these microscopic circulating currents. Even elementary particles, like electrons and protons, possess an intrinsic magnetic moment that cannot be separated from the particle itself. Since you cannot isolate a magnetic charge, the unbreakable circulating current loop remains the fundamental building block of all magnetism.